Right. So I want to begin this talk with some, well, returning to the general philosophy. And the first part of the talk will be rather speculative. So I may say many things that are not correct. OK. So, right. So recall, the philosophy was that for F, a global field, the geometry of GLN over F somehow near a boundary component, or mod Eisenstein, should, in some way, which we were making specific when n is 2 and the field is Q, give you some information on the arithmetic of GLN minus 1 over F. So that's the philosophy. This is the philosophy with Fukaya and Kato. So I guess. OK. So let me say a few words about what one would need, since now we've seen what all of the ingredients we need are in the case that F is Q and n is 2. So in terms of geometry, right, I guess the first thing you need is a space of modular symbols. So in particular, we would want cuspidal modular symbols with, say, ZP coefficients or some such thing. Let's call that S, which should be the homology, some homology group of a locally symmetric space corresponding to the level, or Ruha-Tietz building for GLN or PGLN. Right, so that's the first thing. So the second thing, you need a boundary component in this locally symmetric space, or, well, maybe I should say, or arithmetic quotient of here. So quotient by some congruent subgroup. So we want some sort of boundary component so we can specialize at the boundary, which is supposed to give us the sort of this direction here. For that, we need some sort of compactification. So, for instance, we want a maximal parabolic in, say, GLN with Levy GL1 cross GLN minus 1. Would take it to contain the upper triangular matrices. Should give us a boundary component. I guess components quotes here. So some piece of the boundary of a Satake type compactification of our arithmetic quotient. Well, I mean, yeah. So I mean, there are many Satake compactifications in the number field setting of your locally symmetric space. Yeah, which one you want for modular symbols is a good question, but generally you want the boundary to be fairly small. So the idea somehow is that the boundary components, should look something like Yeah, so such a boundary component should look like the locally symmetric space for GLN minus 1. That's the idea.
So the whole compactification is what? It's
right. So for each parabolic, you add some.
but what's
Yeah.
the total thing? It's not smooth, or it's
Not necessarily smooth. Right. No. I mean, right. Yeah. So I mean, in general, what you do is for each you add some.
so it's a topological space.
Mm-hmm.
Is it anything more than a topological space?
At present, it's just a topological space. Yeah. So I'll mention later that we've constructed these in the case of function fields, but just as topological spaces. They're compact.
And the additional things you're adding is something to do with the symmetric space for the levy? Or something? The
Right.
things you're adding in this compactification
Right.
has something to do with the symmetric space for the levy.
Mm-hmm. Right. That's right. So.
Presumably, you could tell us what you're doing in terms of Eisenstein. What you're going to be taking something from the boundary.
Or how about GL2 over an imaginary quadratic field? Like, how does so then?
Well, GL2 over an imaginary quadratic field, it would just be your usual compactification where you throw in a point for each. Yeah. Yeah. Cusp. Yeah. But. Yeah, so you want the boundary to be sort of as small as possible. Yeah, I mean, I'll say more about this later. But yeah, the idea is if you have a, then you can take the graded quotients, and for each one of those, you sort of take the set of all sort of norms on the graded quotients, and that gives you some. The tuples of those gives you some point in a boundary. But okay. Right. So then one might hope that. So all of this is speculation. I'm not going to claim that you can prove anything in general. The specialization. You can ask whether it's Eisenstein in some sense. So in what sense? Yeah, you were asking about Eisenstein. So I had some GLN minus 1 representation, which gives me some cuspidal automorphic form for GLN minus 1, then you could form an Eisenstein ideal in GLN. Its coefficients somehow come from the product of the zeta function times the L function of this automorphic form, and that gives you an Eisenstein ideal. And you could ask whether the specialization is Eisenstein. So right, maybe I should write that. So cuspidal automorphic representation for GLN minus 1 or form, say, goes to an Eisenstein ideal IF in the A Heck algebra for GLN. Okay. So and what about modular symbols? Because I said you have a space of modular symbols, but what about actual modular symbols in this space? So somehow, I mean, if you're in d minus n minus 1 of this space, then somehow a torus gives rise to a sort of a standard modular symbol. And then you can translate it by the group. And this gives you an analog of the integral points, analog of the Monin symbol. So all of the examples of, say, that I mentioned in the first talk, like Ash, Rudolph, Cremona, Teitelbaum, of Monin symbols, are found in this fashion.
So this is
Yeah.
a cohomology class in which cohomology group?
Cohomology class? These modular symbols, you mean?
Yes,
They're homology class, yeah. Yeah, so probably, I'm trying to be purposely vague, but yeah, but HD minus 1 of my compactification, n, sorry. Sometimes call it D. Something like that. Whatever you've added in. X bar minus x is the boundary. So this would be where did I say you need a yeah, x bar. Okay, so one problem with this is that the way you prove that Monin symbols generate a relative homology group like this is you use the fact that your ring of integers or your of your field is Euclidean. So in general, these things won't generate. But there should be some way around this by passing to some limit over levels.
In general, you can't prove they generate.
In general, they don't generate. Yeah, pretty much whenever it's not Euclidean, they don't generate.
How do you see that?
Well, the proof doesn't work, but I mean, Cremona's students, for instance, in their theses checked this for non-Euclidean fields in the GL2 over imaginary quadratic fields case. They gave explicit sets of generators, which
So precisely,
yeah.
You're talking about the hyperbolic three-manifold, this would be us. And you
Right.
Modular symbols that are Eisenstein still. So you're coming from the cusps.
Right. You take.
Simply the fact.
Well, no, I'm not saying in the Eisenstein. I'm just saying the whole group. They don't generate the whole group. They might generate the Eisenstein part of the group, the Eisenstein component. But you take the path from.
The modular symbols don't give you the full cuspidal, the full amount.
The modular symbols do, but the Monin symbols don't. So I'm translating here by like let's say that the standard path was called 0 to infinity, which it would be in that case. And then I'm going to translate this thing by GLNO, and those things don't generate.
Sorry, what's the difference between that and the modulars?
So a modular symbol would be an arbitrary thing like alpha beta, right? Right, where alpha and beta are cusps in that case.
That makes sense in these high-dimensional cases.
Okay, but here, example, GL2 over K imaginary quadratic. Yeah. Right. But you know, for GL3, you can think of your identity matrix in GL3 as somehow giving you a modular symbol. Uh-huh. Yeah.
Really, Hn minus 1 if you're over a general field F, or does that come?
Yeah, I worry about that actually, but that's why I didn't write it. Yeah. Mm-hmm.
If over Q, if I was over Q,
Right.
then do you know that these modular symbols generate Hn minus 1 X bar version?
Yeah, I think Ash and Rudolph proved that. Yeah. They have some analog of the Euclidean algorithm, which uses the Euclidean algorithm for proving that these things generate. Yeah. Okay. So now.
It's not related to the number of cusps in the class number. Is that entering something?
Yeah, right. The number of cusps relates to the class number, right? But
Is that where the issue lies?
in part, but even if the
Anyway.
I think it's worse than that. Yeah. I think it's worse than that. Okay, so arithmetic. Okay, so we attach to our f. F is okay. We want. I'm assuming our f comes from a Galois representation, which is modular in some sense. Okay, so TF is a lattice in a n-1. We'll need this dimensional Galois representation corresponding to f. Okay, and so this TF, I think, in our previous notation is sort of like theta inverse. Right. So we have Galois cohomology. We may need to take some Selmer complex with coefficients in some twist of this TF. This F here means Selmer. OK, and S should contain the ramified places, and P, places over P. But really, we just want the places over P. So there's different ways to deal with this. One way might be that you want your condition to be unramified at places not dividing P. Anyway, so you modify your H2 group in some way to get the group that you want. GFS means Galois group of the maximal unramified outside S extension of your global field S, F. And then really, to get speculative, you would want special elements in this H2 somehow that arise as specialization. And in general, we really don't know how to construct these things, but yeah, this is all speculations, right? So what I'm describing is if you wanted to formulate this in some general setting, what would you imagine you must need? And OK. Right. Boundary of elements of Euler system for GLN. Whatever that means. There's many problems with this that you should probably see immediately. OK, and then this would give us our map. OK, like that. Yeah, I played around with that. It's just, no, not really. I mean, I had a 2 twist before, but I had somehow twisted my original T so that one of the twists was incorporated, and so I would have had a 1 here. So I could have done that here, but I decided the F should this thing should somehow correspond to like ZP theta inverse, and then that gives you an N twist here. OK. Oh, why? OK. Y was the arithmetic object. I'm trying to use the notation from the previous talk. So then the question, of course, you would ask is, oh, well, is there a map upsilon?
Sorry, is it supposed to be clear why, if these special elements arise as a specialization, that whatever this means,
right?
You should give a map like this?
No. No, I mean I wrote it again.
In particular, S1IS should be almost isomorphic to Y.
Right.
Right?
That's the hope. Almost isomorphic to Y.
So even without knowing what the above statement means.
Right. Right. I mean, the idea is that you would hope that these elements would be parameterized in some way by the same thing that parameterizes the Monin symbols. Like, for instance, I think I mentioned last time, you could imagine that for GL3, that, right, the specializations, OK, so right, so for GL3 and GL2, the specializations are cup products of 3 Ziegel units, GU, GV, GW. And then you have Monin symbols of Ash-Rudolph. And so you might hope to have a map like this. Now, I don't know any Euler system for GL3, so I can't say that this is any specialization. But these are the specialized elements, right?
I don't understand why you need to mention Euler systems like with it.
Yeah, that's why. OK, I don't.
It's a simple question whether that map depends on that.
I know. I just like nice elements. Mm-hmm.
We want to be able to compute.
Oh, yeah. Yeah. Well, I plan the talk to get a little more less speculative as we go along.
The attached work, working has
Right.
explicit Galois representations that you can see are attached to various cohomology.
Right, right.
So then presumably whatever you're saying
Mm-hmm.
can be checked.
Yeah.
I mean, what other
Mm-hmm.
evidence would you have of geometry?
Yeah, I don't know. Well, let me say something more. Okay, so this TF, remember this TF is just like some in the case we dealt with before, is just some like some twist of ZP. So, but we found this twist of ZP as some global quotient of some Galois representation which came from the cohomology of GL2, right? Yeah, mod Eisenstein ideal. So the next thing one would hope for is that you would want an exact sequence of some. Now, it may not come, it should come from cohomology, but it may arise as some sort of subquotient of a cohomology group. This S should be some sort of local quotient of a cohomology group. So it's sort of a global exact sequence. And this thing, so with GQP, at least a partial splitting of some sort, maybe on some piece of this, corresponding to whatever Selmer condition you want. And so this should give you some map. The cocycle attached to this thing should give you some, or the connecting homomorphism attached to this thing should give you some upsilon. And so then the question you could ask is, of course, then what is this? It may be one, or it may relate to the derivative of the residue of the Dedekind zeta function at 1. And the question you could ask is, does the sort of derivative of the p-adic L function, if there were one, for f intervene here in actually trying to prove that it's whatever it is? So now I guess the question is, where should these Galois representations and special elements arise that you need? And of course, the obvious issue is that for number fields, these locally symmetric spaces, in particular, they could be odd dimensional, so they're in no way coming from varieties or schemes. So for number fields, so where should Galois representations, special elements come from? So over number fields, well, you need something which maybe you need a Shimura variety. Let's say, let's now restrict to totally real or CM. You might look to GSP2N or UNN, perhaps. Even there, you're going to have problems. But or GUNN. But the point is, you need you would want a sort of a levy which looks like GLN. I mean, which has some factor that's like GLN. And special elements are really hard to construct, but you might hope to find them as sort of extension classes in some sort of compactly supported cohomology. And I mean, which can be done for cyclotomic units, but okay, in the compactly supported cohomology of modular curves. Well, maybe this is just too hard. So let's ask about function fields. What about function fields? So here we live in an ideal world where all of these things exist to an extent. So let's suppose P doesn't divide the characteristic of F. And N is an ideal in A, where A is the ring integral outside a single place infinity. And let's let S be the n minus first homology group of something I'll define, Bruhat-Tietz building, ZP coefficients. So this thing is going to be the quotient. Got to remember to write n. I have a lot of d's written here. OK, PGL n. AF, like Adele's outside this one place. And then you have the something which I still have to define here. And then here you have K1 of n, where K1 of n will be the inside the product over all places not infinity of the PGL D valuation ring at V of the matrices with bottom row sort of 0, 0, star mod n. Some PGL, so I can use star. OK. It's PGL, so I don't think it matters, but I could write 1 if you like. Yeah. Right. Does it matter? Yeah. I mean, I could just multiply the matrix by some, yeah, something to make the bottom entry 1. But OK.
Why do you write K1 not K0 on this?
Oh, no, we want 1. Yeah, OK. Yeah. Well, when I deal with no, it should matter here too, so I must be confusing something. But when I go to Drinfeld modular varieties, I'll really want a point of order n later. OK, so right. OK, so this thing will be some compactification of a Bruhat-Tietz building. Well, partial compactification, sorry. Given by sort of with F rational boundary. So in fact, were compactifications, true compactifications of these Bruhat-Tietz buildings given by Werner and Jardine and Langvogt for right, which are just compact. Now these things are not compact, but the point is they're good for taking quotients, right? So you take the quotient by a congruent subgroup, you get compact space. It's like, you can compactify the upper half plane by adding an R union infinity, but that's not good for taking quotients. OK, so what is this? Btn is the Rotitz building for PGLN O infinity. So it's a geometric realization of a simplicial complex with sort of D chains of O infinity lattices in K infinity to the n as the D simplices. So O infinity is the valuation ring in K infinity of index. What I mean is you take a chain of lattices L, I don't know, L0 to L D minus 1, and these are full rank lattices, and you want the index of Li and Li plus L, maybe I minus 1 and Li to be Q infinity, the order of the residue field. O infinity mod, I don't know, the uniformizer will call pi infinity. And then these are sort of up to scaling. So up to homotheity. Okay? So those give you the D simplices. For D between 0 and n. Oh, and I need one other condition. I need that. So for the uniformizer, pi infinity L naught should be contained in all LJs. Right? So we don't want the difference somehow to be more than multiplying by the uniformizer. So that gives us the tree I drew in the case of, well, maybe I'll draw it again later, in the case on the first talk for PGL2. OK, so where do we get, so that somehow the class of the standard, there's a standard apartment. Which somehow comes from looking at all lattices of the form, you fix some basis, right? You fix a standard basis, and then you take all lattices of the form pi I to some Ri O infinity with respect to this basis. I guess, and let's put the EI, standard basis. Right. So it's the set of, well, the vertices are this, right, for all Ri. OK. And this is the union of two rays I drew on the Rotitz tree. And then what you can do is you can translate this thing. So this gives you the standard modular symbol, or the analog of 0 infinity. And it's going to be in Hn minus 1. Boundary ZP. And then you can translate by PGLD A, right, to get Monin type symbols. OK. But the problem is, of course, these things again may not generate it because my field may not be Euclidean. Yeah, I guess that would be like an arbitrary apartment. But yeah. OK, so Yeah, and so Kono and Yasuda actually studied these symbols in some sort of equivariant. They didn't have the compactification, so what they did is they looked at some equivariant cohomology group of the compactifications of compactification of Werners, and they showed that in some sort of limited situation where you can, instead of translating by PGLD of A, you can translate by PGLD of Adele's outside infinity. They get a lot of symbols there, and what they show is that somehow these symbols generate the image of a homology of the compactification, the equivariant homology of the compactification inside the Borel-Moore or relative homology. They at least contain that. They didn't show they generate the whole group, but yeah.
Sorry, in this description of the apartment, like
Mm-hmm.
all the pies are just pi infinity, right? For the different pies.
Oh, yeah, thanks. Okay, so right, so now now we need, so these give us modular symbols, but we still need Galois representations, and those are fine in this setting too, because we have the Drinfeld modular scheme, which for our purposes we just need over A 1 over n, which is good. And this parameterizes if you like, its points are over an S, over an A1 over n scheme, rank n Drinfeld modules plus a point of order n. Okay, so rank, thank you, n. Yeah. So right, I mean, so it helps. So a Drinfeld module of rank n over S and A1 over n scheme right, so 1 over n, I mean invert, n is an ideal, right? So I'm just inverting all, right. But I'm writing it that way, okay. So it's a line bundle and a map from a homomorphism from A to the S endomorphisms of L, such that for the Frobenius, which we view as a map from L to LQ, Q is the order of the constant field of F. Okay, then phi of A can be expressed as a sum, if you like, a polynomial alpha I tau to the n, where alpha I you can view, alpha I of A, I guess. Alpha I is a, no, it's some alpha I, which depends on A. Where alpha I is a map from LQ to the I to L. So, and we want, so alpha 0 of A should be A, and alpha n of A should be nowhere vanishing. So it's really exactly degree n, and not some sort of, otherwise you have something which would be like a generalized Drinfeld module. Oh, that's it. Yeah. Tau to the I. Yeah. Great. And what's a point of order n? Oh, I just erased the. Yeah. Okay. Go to another board. It's better. But I can write. Maybe I can write the point of order n here. So the point of order n is an injection of A mod n viewed as a constant scheme over S into L over S. Okay, so in work in progress, we are working to construct toroidal compactifications. So this.
When you say embedding, what structure?
Right, as line bundles, I guess. Over.
Surely you want a module.
Oh, A modules, yeah. Right. Oh, yeah. Preserving the structure given by phi. Yeah. Yeah. Okay. So this thing. So the idea is to construct a toroidal compactification, or actually many toroidal compactifications. Of y1 and n. And the hope is this should be dependent on some cone decomposition. Let me pretend there's just one. And then the object we want for dealing with cohomology, for getting our Galois representation, would hopefully be this thing. I'm going back to the n. Going back to the notation of the previous talk. And twisting. But really, we should take some sort of limit of this over different toroidal compactifications. Okay, so then there's a lot of stuff. Again, I get to the point where I have to get speculative again. Should give Galois representations attached to cuspidal automorphic representations of PGL and F. With certain properties. That is, or supercuspidal, I guess. Whatever that means. And with finite order centric. Steinberg? That's what, okay, what? Yeah. No. So I guess that Flicker and Kazhdan constructed these Galois representations in sort of compactly supported cohomology, but not a single compactly supported cohomology group. If they knew vanishing of certain compactly supported cohomology groups, then it would be in a single one. Otherwise, it's in some virtual representation coming from an alternating sum. But at least for n equal 2, this really does work. OK, and then we don't need to construct a toroidal compactification because it's already compactified by Drinfeld. So that's what it should have. Should also have S as a G F infinity local quotient, just as in the setting of modular curves. OK, so now when I say S, I have to tell you which precise compactification and which precise toroidal compactification. But yeah,
What was that?
S was the modular symbols of S. Sorry, S. Yeah, I didn't. S is this. Yeah. So in our paper on compactifications, yeah, we actually construct two different compactifications, and I think the one we want is actually between the two in general. OK.
So this,
Yeah.
why do you decide to use the toroidal compactification? There's no minimal compactification?
Well, we want it to be smooth. We want
I want it to be smooth for some reason.
so we can, yeah. Well, I mean, we figured.
Usually with the toroidal compactification,
Mm-hmm.
as you refine the curve decomposition, the cohomology group grows and grows with all
Right.
sorts of stuff you're not really interested in.
Right. Yeah, I mean, so even you think the Galois representations for GLN minus 1 can be found as local quotients, I mean, as Eisenstein quotients without.
No, I
Yeah.
suspect the things together sort of
Mhm.
probably just.
Mm. Well, anyway, this is what we're.
I wouldn't be surprised if they were somewhere in the cohomology. I mean, I don't know about this particular degree.
Right, right, right. Yeah, so we want it in this particular degree so that we can do everything. We're trying to make it as analogous to the original setting as possible, but yeah, may not always be possible. Maybe also, yeah, we want the boundary to look like the toroidal compactification, or the Drimfeld modular variety in dimension n minus 1. And the reason is the next thing. Kato constructed, I guess this is unpublished, but I believe it was him.
Sorry, can I ask you?
Yeah.
I guess I don't really understand toroidal compactification in this. I mean, usually when you take
Mm-hmm.
when you do a Shimura variety,
Right.
you take a parabolic subgroup. Its Levy component splits as sort of two parts, which people call the Hermitian and the linear.
Mm-hmm. Mm-hmm.
And the linear part controls the sort of combinatorics of
Right.
the divisors of
Right.
infinity.
Right.
And the Hermitian part
Mm-hmm.
sort of tells you what variety.
Mm-hmm.
For the Hermitian part, you get the Shimura variety or some bundle over
Mhm.
occurring
Right.
in the boundary. But in this function field case, I guess I don't really know how you distinguish Hermitian from.
Right. I am not sure I have a.
nothing in the-
Without reviewing, I can't give a good answer to any such questions, I think. But I will say that, yeah, the toroidal compactifications are rather more complicated than, because the monodromy is more
What do
complicated.
the boundary divisors look like?
Yeah, let me not answer right now. OK, so the Ziegel units. So Kato constructed Ziegel units on the open thing, GU, say, n, and O, Y1, N, N over A1 over N, if you like. And they're constructed in much the same way as Ziegel units on modular curve. And they have the property that, actually tensor Q, they have the property that their integral, when I raise to the qn minus 1 power. So Kondo and Yasuda constructed an Euler system. So I've simplified the Ziegler units by taking y1 as opposed to just y of n, where you would have index with n, an n tuple. So for those more general things, they constructed an Euler system of n-fold Steinberg symbols of Ziegler units. And they computed the regulator on them. In fact, they construct a map which essentially, S goes to kn y1 of n, I guess tensor Q. In essence, what they do is this, S is, so I have to, really I should take not cuspidal symbols, but relative to the cusp. So we can just call that M, relative to the boundary. And so you would have a n tuple, which gives you a symbol which is given by translating the standard modular symbol by the appropriate matrix. And this thing would go to GUGN. So they really already construct the Kato type map. They don't, they're dealing with y of.
So what was M again? Capital M?
Oh, I just needed, what did I call it? BT bar boundary ZP. Hn minus 1. Right? Just the homology relative to the boundary as opposed to the homology of the compactification. So, which is independent of the compactification.
Right,
Yeah.
symbol U1 to UN means?
Yeah, so I take a matrix that looks like star, 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 U1, well, say C1 to Cn, where U1 to UN is C1 to Cn mod n. Something like this. I guess in SLNA. Just like in the Monin symbol construction. So the point is,
And then that's well defined. And you act on that by this.
it's well defined because this is for BT bar for the arithmetic quotient by the particular congruent subgroup, which has 0, 0, 1 on the bottom row.
But how do you check the relations?
So so they do this by the regulator computation, in essence. Right? So you don't know, it's not obvious that it's well defined, but the point is that its composition with the regulator somehow, which lands in a similar group, I guess, or is given by multiplication by some operator valued function. Yeah.
Regulator means kind of L-adic regulator,
Uh,
where it's different from the characteristic.
Yeah, or maybe just C, but in their case, over C. But you have to have some embedding,
So when you say compute
it's complex, right?
you take a regulator map out of Kn.
Right. And then you compute, actually, I'm describing roughly what they do. And you compute compute the composition, right? Like, so if I take, or in other words, they compute the regulator on one of these things. Yeah.
But that's independent of what you want to, I mean,
Yeah.
there exists a map of this type.
You have to imagine, yeah, I mean, I'm not sure I'm accurately describing what they do, but one could imagine that like what happens in the case of modular curves is you end up in, you compute this, but I mean, essentially the image of this regulator is like M tensor C. The regulator actually lands in something like that. And so, and then the map is given by multiplication by some value of an L function with coefficients which are like Hecke operators. And the point is, because it's given by multiplication by something like this, then in the regulator you can show to be injective, then you get that this is a well-defined map. I mean, that's the idea, I think.
In this
Yeah.
function, there are no relations. It would be the other way. Relations.
No, there are relations on the. I guess he's asking.
Like they're all these guys inside that
Yeah.
homology group satisfy those.
They satisfy Monin type relations. So,
That isn't required for this map because.
How do you define the map?
right, it has to factor through homology, right?
Oh, you're not talking about checking the K theory.
Yeah.
Yeah, I'm just
Yeah.
asking about checking their factors through homology.
Right.
And this tensoring with Q,
Yeah. Mm-hmm.
that sounds very undesirable.
Well, I think that yes, it's not totally desirable, but the point is that it should be okay to tensor with Q when you're at the level. The problem with torsion is going to arise when you try to work mod Eisenstein. Until you do that, it should be fine to tensor with Q, as long as you can control the denominators.
Projective varieties over finite fields
Mhm.
with the K groups, I think, are simply torsion.
Mhm.
So
But this is not projective.
it isn't projective, right? But so
Yeah, but I mean, okay, here's a way to deal with the tensor Q. I mean, we know that choose a P that doesn't divide Q to the n minus 1. Then it's integral, because all the Z units are integral. Yeah.
This variety,
Uh-huh.
does it have dimension n? Or
N minus 1, I think.
minus one?
Yeah.
So this is the middle dimension.
Yeah. The middle dimension. That's where you would hope the Galois representation occurs. Okay, so now oh yeah, so what else do I have to say? Oh, good. Okay, so now I can get even less speculative. I started out extremely speculative, and I got to fairly speculative. So now I can say what's proven. Right. So let's talk about n equal 2, f equal f qt. And now here p does not divide q. Okay. So in this case, everything is very nice and behaves very well. So our group delta can be a mod n mod f cubed cross. Characters which, and let's suppose here that also that p does not divide, just for simplicity, I think, because I haven't checked things other cases, but right. Sorry, delta. Otherwise, I'm double counting. Okay. Oh, that's a 2. Okay, so characters, p-adic characters of delta, like theta, it's going to look just like the modular curves case, which are trivial in FQ cross. Characters of A mod n cross, which are trivial FQ cross, that's like the analog of being an even character. Okay, and I want it to be primitive as well. So not factor through any quotient. Okay. Right. So in this case, we have the tree, Ruha-Tietz tree, right? So I can draw it again. So pi infinity now is going to be T inverse in FQ T inverse, which is O infinity, which it sits inside F infinity, which is FQ T inverse. Notice this doesn't contain A, which is A is FQT. Okay. So right. So the vertices are rank 2 lattices L in F infinity squared mod scaling. So these are O infinity lattices. And the edges are tuples L contained in not equal to L prime, such that L prime L is Q. Mods scaling both at the same time. Okay, right. So for example, if Q is 2, I can just draw a little part of the tree. Here I would have O infinity squared as one of the vertices. Here I would have, say, pi infinity O infinity plus O infinity with respect to the standard basis. Here I might have O infinity plus pi infinity O infinity. And in the other one, I guess I would need something like, with my standard basis, pi infinity sort of E1 plus E2 O infinity plus O infinity E1. Okay. Something like this. And then, of course, I have an action on my tree in general of PGL2 F infinity. And the stabilizer of this vertex is PGL2 O infinity. And the stabilizer of this, is it this one? This edge is the Iwahori subgroup of matrices which are upper triangular mod pi infinity. Okay, so what's an end? Actually, I should say this correctly this time. The end is a ray which starts somewhere in the tree and then continues on forever in a given direction. So that's called an end. And the ends are like the cusps. So you compactify the tree by adding in all of the ends. But we don't want to compactify the tree. We want to compactify the arithmetic quotient of the tree. So we should only add in F rational ends, FQT rational ends. So, so BT bar is BT union F rational ends, which are in one-to-one correspondence with P1 of F. And explicitly, you can imagine that, that any end has the form, for sufficiently large I at least, AI comma BI sorry, I changed my notation a little bit, plus O infinity squared. So these are the vertices along the end. And then you take the limit as I goes to infinity of the pair AI, BI, and P1 of F, F infinity, and that is the corresponding end. And then you take those which are rational. OK. And then so this thing has an action of PGL2F. And then we can take gamma 1n, right, which are the matrices which are congruent to maybe what I need is 0, 1, 1, star, star, or something. Yeah. Oh, it's just like this. Anyway, and that will give us our BT1 and bar. OK. So again, we have a standard. So the modular symbols are just you take two n's and you take one minus the other, so you get a path along the tree from one end to another. And so h1 then of bt bar n relative to the n's, the CP coefficients, if you like, is generated by alpha beta, where alpha and beta are in P1F. So it's like a union of two n's. OK, but we have, of course, the standard class, which is the class of our standard department, which is just 0 to infinity. And you can check that it's the same as what I wrote before. And of course, we could translate this by elements of gamma 1n to get a Monin symbol. And then again, I'll modify the Monin symbol as we did before. And so we'll have a Monin symbol UV will be like d over bn goes to c over an, where a, b, c, d are in SL2a, I guess. And CD, or UV, is CD mod NA squared. And these things generate, and they satisfy. In fact, this is proven by Teitelbaum. They generate, and they have the same, give a presentation with essentially the same relations. Generate with relations. The relations now are such that I can throw in any A in FQ star here. So they're kind of like the plus part of the homology I had before, minus VU, and then U plus V plus U plus V, V. So just pretty much like before. OK, so great. So what I want to do then is I want to take S naught to be the homology relative to non-zero n's, and you can imagine how those are defined. So this will correspond to the UV with U and V not 0 here. Here the UV should have GCD1. This should be an A mod NA. OK, and the homology of the actual, so S, which is the homology of the actual compactification of the arithmetic quotient, is is in fact isomorphic to the space of ZP valued cuspal automorphic forms that are, I guess, Steinberg at infinity. I guess it was originally called special. And this identification somehow comes through, in fact, this is a canonical sort of isomorphism. And identification comes through somehow harmonic cochains, which are just like ZP-valued harmonic cochains, which are somehow cuspidal ones, which are somehow functions on these, just on the vertices, which have various properties of summation. And cuspidal somehow means supported on only finitely many vertices. OK, and so we also have an action of a Hecke algebra, H, right? Cuspidal Hecke algebra, and so it's generated by T of A, where A is an ideal. A is an ideal, and then diamond operator J, where J is in, I guess, delta is all that matters. OK, much as before. So from this, we can, of course, then form an Eisenstein ideal. But let me switch to what we have on the arithmetic side. So there we have the Karlitz module, which is just the Drinfeld module T plus tau, rank 1 Drinfeld module. And this somehow, right, so the n torsion points of this module are the sort of analog of 1 minus cyclotomic units in abelian extensions of Q. So the n torsion points of this thing, there's some exponential also, Karlitz exponential, and you can view them as x of pi u over n for pi some transcendental element. But we could also just define them. In fact, they have a very explicit description, which looks like it shouldn't be nice, but this thing. Right. So this is these are actually called cyclotomic units, I believe, and they're not quite units though, in general. Yeah. So u is just an integer prime to n. But all that matters for our purposes, well, it almost only matters up to u mod n. OK. So En, which is given, this is like the nth cyclotomic field, F adjoin lambda 1 over n. This is abelian over F, and with the Galois group is A mod n cross. And so if A corresponds to sigma A, so A sigma A in the Galois group, then I guess this is Hayes here. Sigma A lambda 1 over n is lambda A over n. It really does only depend on mod n. And in particular, if I let En plus be the largest subextension, it's the FQ cross fixed part. So this is an n infinity. It's unramified outside n infinity, in which infinity splits. This is the analog of the maximal totally real subfield, because that's where infinity splits. Infinity is the analog of the real place. Right. that's right. So that's the analog. In fact, if I take something in FQ cross and I ask how it acts on lambda 1 over n, well, we have one description, and there's a second description, which is it's just C lambda 1 over n. So all these nice properties. OK, so of course, now we can consider cup products of these things, or Steinberg symbols. So we could look at lambda u over n cup lambda v over n in H2 on. Oh, yeah, so I should say these things are 1 over n units. So they're not just field elements. They're these are, sorry, n units. And in fact, if n is prime, then they're true units. So again, you have that analogy with, no, sorry, if n is not prime, then they're true units, not a prime power.
O n is A.
Huh? What?
O sub n in that class.
Oh, A sub n. Thank you. A sub n is the ring of the integral closure of A in En. In fact, these land in the plus part, but I'm just going to take the theta component of this, which we fixed a theta at the beginning, and let me call that y. So I'll project to that. OK, so inside my cuspidal Hecke algebra, I was saying I have an Eisenstein ideal. Y doesn't directly relate to a class group anymore. It's really just the H2, the K2. Yeah. OK. So this is going to be generated by TL minus 1 minus n of L for L in A prime. I guess not dividing n, but we'll just take to be 0 if L divides n. OK, so define in the same way. And then it turns out that H mod I in this theta part, so now for the action of diamond operators, inverse diamond operators, just as before, is ZP theta mod L theta minus 1. So this is what we'll call lambda theta. This is what I'll call xi theta. And L theta s here, the L series, which gives you this L value after analytic continuation, is or P not dividing n, 1 minus theta applied to Frobenius at P inverse. Or maybe I just take, norm P to the minus S inverse. OK. So again, on the Grimfeld modular curve, as I already mentioned, we have Siegel units. So we have y1n inside x1n, Grimfeld. So I won't take a break today. I'll just finish in soon. Modular curve. Inside, right, and its compactification. Over A1 over n. Then I have GU over n inside O y1n cross. And in fact, again, so how do we prove that? So we can construct a map following Kondo and Yasuda. S naught goes to, sorry, I wrote the wrong thing. H2 y1n with ZP2 coefficients. And then we have infinity on the tree, not infinity the place, but infinity on the tree. We can do specialization at infinity, just as before. It works for H2 as well as K2. And this will go to H2 ON 1 over n ZP2. So this is some map Z sharp. UV here goes to GU cup GV. We chose P not to divide Q squared minus 1, so I don't have to worry about denominators. These things are real integral elements. And then it turns out that these things specialize at infinity to the Karlitz cyclotomic units. And so this is well defined by the regulator computation of Kondo and Yasuda, suitably worked out in our case. And Eisenstein, because infinity is Eisenstein. So, right, well defined in Hecke equivariant. By Kondo and Yasuda. And Eisenstein because infinity is Eisenstein. So, OK, so that gives us a map var pi. It turns out that on theta parts, because we chose theta to be primitive, S naught theta is S theta. And this thing, H2, oh, I defined y wrong. Well, it doesn't matter because H2 ON 1 over n ZP2 theta is just H2 ON ZP2 theta. So, and this is, we can take to be y. OK, so we have var pi for upsilon. We can take t, which is this. And Drimfeld already constructed the Galois representations, which are special at infinity or Steinberg on this thing. So this is already ordinary in the sense that we need. That is the sense that we need. So no need to take any ordinary part. And so there's an exact sequence, T sub, T quo, Steinberg at infinity, special at infinity. The Galois representations that occur in this cohomology, which aren't all of them, right, are exactly those which are ordinary. So that could be taken to be the two-dimensional Galois. Mm-hmm.
It's a condition at infinity.
Right. Right. It's a condition infinity which gives you this exact sequence.
Yes.
Yeah. So this is of H. Right. So that's the cool thing here. Infinity, the place infinity plays the role of the real place and the place at P here. Plays both roles simultaneously somehow in this function field setting. So this thing actually now, we don't need any defunctor or anything. This thing can be defined. It's the graph of the special fiber at the place at infinity. So this is really just our S. And by duality, this is really just H. And remember, S was also just S. So the modular symbols. And then if we look at the divisor, the theta part of the divisor of G1 over n, somehow theta part of this somehow looks like this 0 minus infinity. Maybe I'll put this in quotes. So this gives us the quotient that we want, Q, which is like lambda theta mod. This is global. And then we get an exact sequence. 0 goes to P, goes to T mod IT. goes to Q goes to 0, which is locally split at infinity. You can distinguish the two actions by Frobenius at infinity. So, so the argument's pretty much the one I gave before. And so then we can't just define it as the cocycle because, again, as Ashe was saying, now the H2 isn't really related to the class group. So we have to define it as a connecting homomorphism. It turns out, again, in this case, by theta being primitive, that H2 compactly supported really is, really is just, did I write? Yeah, O is A. OK. Is really just H2. So if we look at the connecting homomorphism on compactly supported cohomology, and this thing is isomorphic to Y. So in other words, what we get is Y maps isomorphically to H2. Then we take the connecting homomorphism to H3. And the way we constructed this was when we went to this exact sequence, the two things switched. This is this mod I, but Q and P switched from T sub and T quo. So really, this P is just S mod IS. And because we have trivial coefficients twisted by 1, H3 compactly supported just gives you the P here, which is S mod IS. I guess we're in the theta part, but maybe I didn't say that earlier. OK, so this is our epsilon. And then we also had var pi. And so the conjecture is that var pi and epsilon are inverse. And the theorem is that Xi prime epsilon composed with var pi is Xi prime, where Xi prime is d dq to the minus s. Yeah, L theta inverse s at s equal minus 1. Yeah, so it's completely analogous to the case of modular curves. And in particular, if Xi prime is a unit, because now it's just a number in ZP theta, where the ring given by adjoining to the, it's just a unit. It's just a number in here. If it's a unit, then we have the conjecture. OK, thanks.